Hi, everyone. Thank you so much for joining us for this webinar in our series, AI Applications in Earth System and Climate Science. This series is hosted by NOAA's Climate Program Office in partnership with the NOAA Center for Artificial Intelligence, or NCAI. My name is Clara Deck. I'm working with the NOAA Climate Program Office, and I'll be helping to moderate today's sessions. To start the webinar, I'd like to introduce Anna-Rita Mariotti. She's the Senior Advisor and Scientist here in the NOAA Climate Program Office, and she'll give some words of introduction.
Thank you, Clara, and hi, everyone. We are very happy to be hosting this webinar in partnership with our sister office, the NOAA Center for AI. And this webinar today is continuing a series that we started in the spring. We had 5 webinars on different aspects of AI application to Earth system science. You can go back and actually listen to those webinars. They're all archived on our website. And this webinar series features NOAA scientists, NOAA-funded scientists, NOAA partners. We really are interested in all types of NOAA-relevant sort of applications of AI. And so the webinar series continues. Today is the first of a number of webinars that we're going to be hosting in the next few months. And we have a good lineup, great lineup for today. Clara will be introducing our speakers. The topics are, we're going to be looking into coupled models based on ocean atmosphere emulators. So that's really exciting and interesting. We're going to be hearing about examples of AI and ML applied to NOAA GFDL modeling for weather forecasting, and also just in general the partnership that NOAA has with many organizations to share its data, model data for training emulators. So that's going to be really nice to understand the value of all this physical model data for AI training, AI validation, etc. So looking forward to the talks. Back to you, Clara, to introduce our speakers.
Thanks so much, Anna-Rita. As she mentioned, today we're going to hear from 2 great speakers. We've got Lucas Harris of NOAA's Geophysical Fluid Dynamics Laboratory, or GFDL, and we have James Duncan from the AI2 climate modeling team. So during the webinar, at any point, please feel free to enter questions for the speakers using the GoToWebinar question feature. If you're comfortable doing so, please indicate your name and affiliation with your question so that I may let the speakers know who is asking and give them some context. I'll facilitate Q&A sessions after each of these 2 presentations. So first, we're going to hear from Lucas Harris, and I'll transfer the screen over to him. So we're going to hear about the work their team is doing over at GFDL on weather to climate modeling using AI and machine learning, and their collaborations with AI2. Thank you so much for being here, Lucas. We're excited to hear about this science, and take it away. Lucas, I think you're on mute.
Sorry about that. Thank you, Anna-Rita and Clara. Thanks for this excellent introduction and this chance to give this webinar to this excellent audience. Thanks everybody for coming today. I want to talk about some of the efforts we started doing here in the Weather and Climate Dynamics Division at GFDL as part of the FE3 team's efforts. In particular, I want to mention two people in particular. Spencer Clark, who works here at GFDL from the Allen Institute for Artificial Intelligence, one of James's colleagues. AI2 has really produced a lot of the technology I'm going to talk about today. I also want to thank Linzhang Zhou, who's really been leading our AI modeling effort here within W Division. Some really fantastic work that he's done. So I want to make sure that the people who have done the excellent work here get the proper credit. So GFDL and AI2 have had a collaboration going back to 2019. This started with what was originally Vulcan Inc.'s climate modeling effort, which was started by Professor Chris Brotherton to bring new technologies to accelerate climate modeling. This originally meant both artificial intelligence and GPU acceleration of models, an effort that I'll talk a little bit more about later. One of the things that both Vulcan and then later as it transitioned to AI2, the Allen Institute, has really done that has made things much easier is that they placed an employee originally 2 employees, now 1 employee, at GFDL to cooperate on SHIELD and FD3 development, and to help our model output that is used to train AI2's AI models be prepared to be able to send to AI2, and to also then help GFDL scientists be able to use the outputs that AI2 has created, both their software and their excellent data sets. So here's an article from NVIDIA's website talking about this. So AI2, originally what they got started doing is they had a vision for a hybrid AI physical model in which you have a dynamical model, you taking the FD3 dynamical core in this case that we develop here at GFDL, and then coupling it to an emulated physics package. And they did some work with that, but their main emphasis was on developing corrective machine learning. And the basic idea of corrective machine learning is that you could take a low resolution model, say 200 kilometer FE3 GFS, which is now SHIELD, and then nudge it to a Corson 3 kilometer X-SHIELD simulation, a global storm resolving model that had very high fidelity moist physics, land atmosphere interactions, small scale processes, and so on. And then you could train a machine learning model on those nudging tendencies and then use it to correct a free running model, a free running 200 kilometer model closer to the 3 kilometer reference state. And this actually turned out to be quite a successful approach. There's a lot of little things you need to fix up with this, but they published a number of different really good papers on this, and they found that even in this very cheap 200 kilometer model, if you did this corrective machine learning, you'd really address some of these problems that have been bedeviling climate models for many years. You could greatly improve the land precipitation, a good 25 to 50% in some cases. The diurnal cycle of precipitation was greatly improved. We had an excellent diurnal cycle in our SHIELD models, including X-SHIELD, and the 200 kilometer model was able to capture some of that with the correction machine learning, and also significant improvements to the surface temperature. So there's a lot of really nice results they published with this, and is a very pushing forward the limits of machine learning and hybrid models. Also, as part of this, they developed a really neat Python wrapped version of what is now SHIELD. And this kind of tied into another effort that I'll talk about later that was an AI effort that eventually transitioned into NASA and NOAA. One thing I do want to point out is a 200 kilometer model, simply just because it's such a lower resolution model, is much less expensive than our very expensive 3 kilometer global storm resolving model, X-SHIELD. In fact, it's about a factor of 10,000. One thing that they then started a couple of years ago is that with respect to what the significant improvements in fully AI data-driven weather prediction models is to start looking at full model emulation of climate models. And the problem with a lot of, especially the earlier generations of these AI weather models, is that they basically fell apart after a couple of weeks, sometimes even after a few days. And that's not going to work for even sub-seasonal prediction, let alone seasonal prediction or climate simulations, which you're doing historical or control integrations. So AI2 has then set out to develop what's called the AI2 Climate Emulator, ACE. And James is going to talk some more about more climate applications of this excellent tool. But basically, the idea is that it's an autoregressive, fully machine learning model. It runs at 1 degree resolution, so about on par with the standard CMIP class model. It's based on NVIDIA's spectral Fourier neural operator. So it's kind of like a spectral model, although there's no active dynamics in it. It's all data-driven. You can train this on a variety of different data sets. ERA 5 is what they started with, but as I mentioned later, reanalysis has a lot of limitations. You can train it on climate models or weather models. So you can do simulations using SHIELD, our CM4 climate model, coupled climate model. They've been working on it with the Department of Energy's excellent SCREEN model, and so on. There's been a number of things that were done in ACE to make sure it remained stable and gave a faithful climate, in particular that exactly conserves air and water, something that a lot of AI models don't do out of the box. And this remains stable and maintains realistic climate variability and trends out for 1,000 plus year rollouts. And that's a really impressive achievement they can do a lot on. And that 1,000 year rollout most impressively takes 16 hours on a new H100 GPU. So you can really do a lot of large ensemble stuff with this very advanced emulation model. You can see 2 examples here of AMIP type simulations of specified SSTs, or the latest results we have from my colleague Spencer Clark here, doing simulations of slab ocean model, and then you can start to look at the climate response under enhanced carbon dioxide. So you can see an example here. It's out of sample, 3x CO2 that's trained on 1x, 2x, and 4x, but the 3x is out of sample. And even then, ACE2 does a good job comparing to a SHIELD 100-kilometer simulation. I should point out this is all open developed, so it's all available in the open. You can go to GitHub or to Hugging Face to download it. And I know a number of excellent groups. Libby Barnes's excellent group at Colorado State, or the folks at UKMO for seasonal prediction are already using this. Now, in our division, I mean, we do some climate things. I mean, we are GFDL. We're famous for doing climate research, but we have a goal of doing seamless weather to climate simulation. And of course, my division, the Weather Climate Dynamics division, is very interested in weather prediction simulations. And having a seamless model is a major GFDL mission goal, in particular because there's so much that can be learned from both scales. I mean, it's all one Earth system. And on top of that, there's a lot of what I call climate thinking that can be applied to improve the weather prediction problem. So what we started was we took ACE2, the most recent version that's been prepared to be able to train on SHIELD or a number of different other systems. ACE was originally trained on ERA5, so we decided, okay, well, what can we do if we use the freely available GFS analyses, because ERA5 is not available in real time. If we want to do forecasts, we're going to use the GFS analyses, which are already pretty darn good. But we found that the results were pretty disappointing when we used the original ACE using the GFS analyses. The forecast skill was quite a bit worse than our SHIELD weather prediction model, or 13-kilometer SHIELD. But the big reason for that is that ERA5 is very different from the GFS. ERA5 uses the IFS, GFS uses, of course, the GFS, more similar to SHIELD. But what we can do is we now have resources available to us where we can start to retrain using the resources made available on Ursa, the new NOAA GPU machine. And what we can do is we had this excellent data set that was produced by PSL called UFS Replay, trained on ERA5, but using the UFS, basically the same model as the GFS with some updates, same FE3 dynamics, same GFS physics. There's 30 plus years of this available. So what my colleague Linzhang Zhou did is he spent a lot of time preparing this data, regridding it to 1 degree for feeding into ACE, and he retrained it to get a model that's trained on the UFS replay that's more consistent with the GFS analyses. And indeed, we found that the skill was significantly improved. And actually, we could go even beyond that. What we could do is that you could retrain ACE starting from an ERA5 checkpoint. Which means that basically you take the version ACE trained on ERA5, and then you do a few what we call epochs, passes through the 31-year set of data, and retrain from that. So not only do you get the good skill, the good dynamic representation from ERA5, but you're also able to fine-tune it or do what's called transfer learning from the GFS analyses so that it gets more consistent with those GFS analyses. So that's, yeah. So you can see from some of the plots here, we're already improving quite a bit upon that original, little bit less great result from the ERA5 trained ACE. A little bit about the methodology, a little bit about getting under the hood. So there's 31 years of the UFS replay data. It's divided into 3 sets. The main one is a training data set, which is 25 years of the data set. That's the ones that's used for basically computing and minimizing your loss function, which is the root mean square error of your various climate variables. And then you use some data to validate it against during the run. You learn a little bit, you check it against the validation data set, and you then use that to retrain it as necessary. Plus a testing data set, which is completely independent, to make sure that to do an independent test of all this. And then what we do is that we do what's called inference, which is a fancy machine learning word that just means prediction model runs. 10-day runs every 10 days for this 3-year data set. This is all being done again on Ursa. We're limited to 8 GPUs using the windfall allocation. And then we validate that and our SHIELD predictions against UFS replay, not that much different from ERA5. The training turns out to actually be fairly expensive. You need 80 hours on 8 GPUs to complete the training from scratch. If you're doing the transfer learning, it just takes 2 hours. The inference, and this is where the real value of the AI models come in, is that it's 20 seconds on 1 GPU, which is far faster than the dynamical SHIELD model. And here's some results from these ACE forecast experiments. I should point out here, there's 3 different things here. One is the observations, the UFS replay we're validating against. We see 3 sets of lines, one for the global, the solid lines, the land surface, dashed line, and then the ocean for dotted lines. And then we show on the top, we show the mean values worldwide or over the different land or ocean. The middle is the bias, the difference between the means. And then on the bottom is root mean square error, the mean root mean square error for the series of forecasts. And we find that for H500, we can get scores that are on par with the SHIELD, already doing a pretty good job. So, hey, that's good enough. Same with 850 millibar temperature, which SHIELD actually does a really good job with already, and yet we're able to match that with this 1 degree model. The real value is a great improvement in things like 2 meter temperature, which is rife with biases, especially from the land model. And this is where the AI models really shine, in that it kind of smooths over all those different dynamical details that go into land modeling. And indeed, we see a big improvement from ACE with this training compared to our SHIELD model for 2 meter temperature. We take a look at other surface measurements. Winds is a little bit better, but you can see a major improvement in precipitation in particular, especially over land, which we're really excited about. This really shows quite the value of learning from the data that's in the that's already been made available to us. And that's basically where AI really shines. It takes advantage of the fact that we have all the answer. We don't have to sort out all the tiny little details, even though there's still a lot of detail to that in the dynamical models. Something I'll mention a little bit about later. So this is already a pretty good result. These are real hot off the press. This is just results that Lin Zhang shared with me the other day. We're still continuing to do some fine-tuning work on this. Everything going okay so far?
Yep, everything looks good. Thanks.
Fantastic. Okay, so a little bit more philosophical in the next couple of slides. So we want to move towards what we call AI SHIELD, a version of SHIELD that is using ACE. We want to be able to go to higher resolution, 25 kilometers. I mean, with 1 degree, you can get good large scale skill, but the amount of information you get out of it's not so much. We want to also add more vertical levels and have more variables, especially clouds. We're very interested in predicting. It turns out that the hardest part is training and the data preparation behind all this. And that's where all the real work goes into. And especially 25 kilometer ACE needs about 16 times more resources, which we don't have quite yet. We're looking for a larger allocation on URSA to do that. Now, there's a lot of things you can do with an AI model because it is so efficient to run. And in particular, when you're training it, you choose your loss function, the things you want to optimize for. You can choose what your loss function is to emphasize what you really want to emphasize. I mean, my salary gets paid by US taxpayers. Maybe you want to emphasize for the contiguous United States, which is what developers that say the GFS are already subconsciously doing. But you can emphasize what variables you want to improve, what levels you want to improve. Maybe you want to improve over a certain part of the North Atlantic for tropical cyclones. You can have different versions of it and so on. You have a lot of freedom of choice there. Plus, you can also do stochastic loss functions, some I'll mention a little bit later. One of the real advantages of the AI models, again, is how fast they are. 1 GPU, a couple of minutes, you produce a member. Well, you can produce huge ensembles, which are kind of the obvious thing. You get a very large spread if it's designed correctly. But I'm thinking even beyond that. I mean, think about huge ensembles. The first thing that comes to mind is data assimilation, which is kind of an obvious thing to do for ML efficient models. Well, that needs more vertical levels, though, to be able to create something that's useful for forecast models. The other thing is rapid what-if testing, which has obvious influence for researchers, but also for forecasters. Imagine having a hurricane forecaster who could change SSTs or move humidity or ridges around, push a button, and immediately get a large ensemble, giving me the uncertainty associated with that own input that may be something wrong with the input data they already have. So there's a lot of possibilities for both research and applications and forecasting. And plus, we can couple ACE to SHIELD. We can have SHIELD fill in the details using large-scale nudging. This is basically what the Canadians are doing a great job at. Or we can even downscale from an AI forecast, something that I'll mention here in another couple of slides. A little bit of less happy things is that there's a few bottlenecks to work out. One is machine learning is, of course, notoriously data hungry. And one thing is that everybody's training on ERA 5, it seems, which ERA 5 is a great data set, but ERA 5 has problems. One thing I like to say is that XSHIELD actually has better clouds and radiation than ERA 5 does compared to observations. So ERA 5 is not perfect. And also the thing to mention is that if you use the same things everybody else is doing, you're going to get the same results as everybody is doing. Common methods get common results, something that I don't think is really realized enough in the rush towards having everybody working on one thing. for the observing system just isn't good enough, especially as you want to go towards increasingly high resolution. I mean, 3 kilometers or even sub-kilometer data. Data isn't there over the oceans or in remote resource constrained areas, poorer countries, or in war zones. I mean, you know, there's a lot of data there, but people aren't sharing that for obvious reasons. And from a more climate perspective, there's only one realization of the past, so we don't get variability of previous years from data. There are no observations of the future, as my former boss, Tom Knudsen, liked to say. So this is where dynamical models will still be useful, and this is where dynamical models follow the 4 C's. They're consistent, constrained, comprehensible, and conservative, which is something that machine learning models are still in their infancy with these things. And of course, synthetic data is all the rage because MLs have eaten all the data in the world already. The problem for large language models, the problem for AI, weather, and climate models too. James is going to talk about some results emulating CM4, one of our coupled climate models here. GFDL has a whole suite that's providing ensembles of increasingly high resolution coupled climate data. And then, of course, our SHIELD, our prediction model suite here at GFDL, they provide 3D output at kilometer scales, and eventually soon we're going to go to sub-kilometers, large eddy scales. You can see an example here published by my colleague Kuan Gao. And you can run SHIELD in replay mode. You can constrain to the large scale conditions, or you can, again, constrain to the AI's good large scales as well. So there's a lot of data we could produce here that could then be fed to improve your AI emulators. One thing I do want to point out is I mentioned a lot of different model names, but they're all slightly different variations on the same code base. All the science, all the infrastructure is exactly the same, where it's all FV3 based, dynamical core, MOM6 ocean model, which we're now using in SHIELD, FMS, and so on. So we're not developing 10 different completely separate models. One example of the great stuff that AI2 is doing with GFDL's data sets is the downscaling experiment. So they developed a new version of ACE, stochastic. It adds random noise, and paradoxically, that random noise, which combined with the probabilistic loss function, actually sharpens up your models. One of the problems with AI models is the fuzz. That AI models, the first thing AI models seem to learn is that if you smooth out your solution, it makes your skill better. And that's exactly the opposite of what we actually want out of our models. So the stochastic model can sharpen that up at 100 kilometer resolution, 1 degree. They're already doing a pretty good job emulating our new XSHIELD, our new XSHIELD 11-year AMIT simulation, a very frontier data set. But if you want to fill in all the scales, you can then do that too using the ML downscaling that AI2 has just developed, which goes from the 1 kilometer all the way down to 3 kilometers, a factor of 32. Trained on our XSHIELD output to really give you the full spectrum of scales. And this is a more excellent work that more new results are coming out seemingly every day on this excellent effort. So we're really excited to see where they're going with this. Shifting gears a little bit, something else you can do with machine learning is physics-informed neural network. We had a professor here at Princeton, Qingyao Lai, now at Stanford, but she was working with an undergraduate Princeton University student working with SHIELD data, specifically 3 kilometer T-SHIELD. And what they did is that they used a physically informed neural network, a physically constrained machine learning model that would then train on 3 kilometer T-SHIELD hurricane simulations. And then you could apply that to observed flight level and dropsonde data to reconstruct an entire tropical cyclone vortex, in this case, Hurricane Ida. This is actually a really neat thing that goes far beyond what traditional data simulation is doing, but is still much cheaper than what DA is doing. This is just one ensemble member, not the full ensemble, but really shows the capability of what you can do with when you're adding the physics to the neural net, to the machine learning algorithms. And finally, I want to mention another AI2 initiated project called PACE. This is a project to rewrite FV3 and SHIELD in a dialect of Python, GT for Pi. That was developed in Switzerland. It's now being used by the European Center and Max Planck Institute. And this allows you not just have one optimized code. You write in stencils with Python. It gets translated into optimized code for individual CPUs, GPUs, all the different GPUs, ARMs, quantum computing, and so on. But it also gives you the power of the whole Python ecosystem, notebooks, instrument your model, adding graphics, AI ML like PyTorch, adding your debuggers, so many different things. And not only does it accelerate your model by allowing you to run on GPUs, again, with the same code that gives you good performance of CPUs. And I want to point out, this is improvements on what is already a very efficient FV3 dynamical core and very efficient SHIELD. But you can go even faster, maybe even up to 10x on the newer GPUs. We almost have a full physics pace working, and we're hoping to have science runs that are ready by the end of this calendar year. And finally, I want to acknowledge the excellent team that does all this work, as well as our excellent partners at the Allen Institute. You can see more information about SHIELD and FE3 at the addresses here, or email me for more information. And James will discuss much more about the excellent climate work that AI2 is doing with ACE. So thank you.
Great. Thank you so much, Lucas. That was wonderful. We'll have a short period for Q&A here, and then we'll do another Q&A at the very end where you can direct questions to both speakers if you'd like. So feel free to put your questions into the question feature. And again, if you're comfortable adding your name and your affiliation with your question, that'd be great to give our speakers that context. So our first question comes from Marcus Pereira, a machine learning research scientist at Bosch. The question is, can this model be used to predict occurrence of tornadoes? And what kind of data do you think would be needed to train such a model that could do that? And also a side note that Professor Lee Orff developed a numerical simulation model to replicate the EF5 El Reno tornado. Can we use these as hybrid data generators? Do you have thoughts on that?
That's an excellent question. And indeed, models like the CM1 simulation of the El Reno tornado are excellent sources of data sets that the machine learning models will need to be able to train on, because simply we don't have observations of those. Now, when it comes to predicting tornadoes, with the model, 1-degree model like ACE, you can predict the large-scale environment that's favorable for tornadoes, kind of like the old-fashioned way of issuing tornado outlooks. For direct simulations, you need something like the downscaling, which is another possibility, and indeed AI2 has worked a lot on that. I know other centers are working on 3-kilometer emulation of high-resolution models as well. So it's a little bit indirect in this case, but the pathway is definitely there for both the downscaled ACE as well as for some of the other methods, like some of the GraphCast-based methods that are out there. So the future is bright. Remember that even at 3-kilometer resolution, we don't actually capture tornadoes. We can only simulate the tornadic thunderstorms. But there is a lot of possibility once we have models that can fill in those sub-kilometer gaps to potentially predict the vortices themselves. I should point out we actually are able to predict something like tornado-like vortices at 1-kilometer resolution with some of the idealized models we predicted. So I want to send a shout out for our research on that. But thank you.
Great, that's really exciting. Our next question comes from Kenya Torid from NOAA PSL. The question is, given that ERA5 is generally considered more accurate, can we still consider the model is okay even if the skill relative to GFS analyses is poor? Also, does fine-tuning to UFS replay potentially degrade the skill?
So ERA5 is considered a very good data set, but it's certainly not the only one out there, and it also has its own problems, as I mentioned, especially with clouds, radiation, and precipitation. And now, certainly, certainly the fact that the GFS analyses, when you initialize the model trained on ERA5, won't give you as good of a result, but that's not due to a skill issue. That's more due to the fact that they're simply just very different analyses. I mean, we could initialize this with European Center analyses, but that's not available for free. I mean, the GFS analyses are available for free, and as I mentioned, those analyses are still pretty darn good, even if they're not world class. I mean, you know, they're the GFS is basically the best available free model in the world. So if you really wanted to get that little bit of extra skill, I mean, you could certainly pay for the ECMWF analyses. It depends on what you're forecasting for, certainly. I mean, GFS has shown better tropical cyclone forecasting skill than the European Center in recent years.
Great, thank you. Another question comes from Panos Athanasiades. Sorry if I got that wrong. This question comes from the CMCC Foundation in Italy. How would ACE compare with SHIELD if the output of the latter is bias corrected?
That's an excellent question. We haven't looked too much into that, but one thing we have noticed is that bias and error don't always project into each other as well as we would like to. And in fact, we've actually seen cases where a more biased forecast can get you a better forecast skill, especially in some of these kind of high impact weather events. I would suspect that, especially for things like 2-meter temperature, it would get closer, but you still see a bit of an advantage to the emulation, in part because it is being trained with the exact behavior of the land surface. Now, with that said, of course, ACE can't get you all the details of that interaction you want, especially as you go towards increasingly high resolution, because it is limited in how much you can go to. But certainly there's a lot of benefits to using the ML model that's built into it, and the physical model, it makes an excellent complement to the physical models, which are already doing a very good job of what they are doing at. But thank you, Panos. It's an excellent question.
Great, thanks. I'm going to do one more question just for the sake of time in this question and answer period, but please keep the questions coming if you have them, and I'll pass them along. So this question comes from Will Yick from the University of Washington. He said, thanks for the great talk. There has been discussion in the community of how to evaluate these AI weather models beyond medium range skill. What types of tests do you think we can do, or do you think we can use to evaluate the physical consistency of these AI models?
Yeah, so there's a lot of things that could be done. I mean, you could analyze how well some of the more S2S relevant variability is captured. I mean, think about things like the polar vortex. I mean, the stratosphere is not super well represented in the AI models yet, but that's one thing that could certainly be looked at. People talk about the Madden-Julian oscillation. I expect you should be able to get a good MJO from this model, although I should point out the physical models have gotten much better at the MJO in recent years. And then some of the more prosaic things about the variability, you think about just like how it maintains like, angular momentum conservation. I don't think is that important, but it's one thing you take a look at to see whether you get a good NAO or some of the other modes of variability as well. Or even just, does it represent some of these variances between, say, temperature and some of the large-scale weather regimes, for instance. So I think there's a lot of things that could be looked at, and those are just what comes off to my mind off the top of my head. But thank you so much, Will. That's an excellent question.
Great, thank you, Lucas, and thank you for all these questions. Keep them coming, as I said, if you have them. And next, we're going to move on to our next presenter, James Duncan. You are now the presenter, so you can go ahead and share your slide. So James Duncan is a researcher on the AI2 climate modeling team. His talk will focus on coupled climate modeling using 3D ocean and atmospheric emulators. We're really excited to hear about this work, and please go ahead.
Yeah, thanks so much, Clara, and thanks for inviting me to give a talk to this great seminar, this great audience. So I'm James Duncan. I'm a postdoc with the Allen Institute for AI Climate Modeling team. Here's all their faces here. And today I'll be talking about the work that I've been doing during the postdoc, which is on Samudrace, trying to do coupled climate model emulation with 3D ocean and atmosphere emulators. And this is in partnership with our great collaborators at M-Squared Lines, GFDL, and other institutions as well. So yeah, I'd like to start this talk off with just a little bit of eye candy. So here in this video, I'm showing a single output field at a 2-meter air temperature from Samudrace. And so you can sort of see that, Samudrace is actually able to simulate the global atmosphere in this way, as well as many other fields. And our goal in this project, and I think more generally in AI2 climate modeling, is to democratize climate science to a certain extent by enabling accurate and computationally efficient coupled GCM simulations on a single GPU. So this simulation here was run on a single H100 GPU over 40 years. And so Samudrace is composed of 2 components, a 3D ocean and sea ice component that takes 5-day steps forward into the future, and has 19 vertical levels. And so our original data, which comes from the climate model V4 from GFDL, had 1/4 degree resolution, which we regridded to 1 degree to match the atmosphere resolution, which is also 1 degree in the horizontal. And the second component is a 3D atmosphere and land surface emulator, which takes 6-hour steps. So you have this difference between the temporal resolution of the atmosphere and the ocean components. The atmosphere has 8 vertical levels from the stratosphere down to the surface. And the real benefit of this kind of modeling that I think Lucas touched upon is that we can do these outputs, these simulations, with much lower energy costs and much faster than a traditional model. So in this case, about 1,700 times less energy intensive and about 50 times faster for an 800-year simulation. But in many ways, we developed this in a way that is analogous to how CM4 itself was developed, with different independent groups that are, known to one another and collaborating in certain ways, but more or less on their own, developing components of the model and then coupling them via fine tuning. So the group that worked on the ocean emulator called Samudra is from M² Lines, NYU, Princeton, Surya, Adam, Alistair, and Laura. They published this work in Geophysical Research Letters earlier this year, and they developed a 3D global ocean emulator, taking 5-day steps similar to what we're using. And this ocean emulator is forced by atmosphere surface fluxes. So those surface conditions are prescribed, they're just given as the emulator evolves forward in time. It includes a full depth of ocean, and they achieved really stable, accurate, like no drift in long rollouts. You can see here, this is a global average time series of the potential temperature at the surface, and you can see that this is a very stable simulation, and also does a good job in terms of the vertical structure, which you can see in this bottom bead plot. So just to give you a sense of what sorts of variables Samudra is working with, I've listed them out here. I won't go through every single one of these, except to note that these boundary forcings, which are just given as prescribed to Samudra, are zonal wind stress and the meridional wind stress. And then they also used a net downward heat flux, which includes the flux of heat below the sea ice into the ocean. Another prior work that Lucas already mentioned is ACE2. So this is forming the atmosphere component of Samudra. Again, many variables on 8 vertical levels, and then 2D variables as well, and a number of diagnostic variables, meaning that they're output only from ACE, but not inputs. And many of these diagnostic variables will be passed to Samudra in order to set the surface conditions when Samudra takes a step forward in time. And the boundary forcing for ACE2 is the incoming solar radiation at the top of the atmosphere, and then also the sea ice, grid cell fraction, and the SST. So again, when training ACE2 in this work, and in the work that Lucas was described, the SST is just sort of given, or perhaps in some cases like a slab ocean model is used. So in our work, we have a 200-year pre-industrial control coupled simulation from CM4 that came courtesy of our collaborator, Bill Herlin of GFDL. And we held out 150 years for training Samudra. We somewhat modified the outputs of Samudra to include the sea ice grid cell fraction and sea ice thickness. And then we also modified how exactly we're forcing Samudra by, rather than taking the net heat flux into the ocean, we separate out each of those fields because those are already diagnostic outputs from ACE, and we'll just pass each of those separately as inputs to Samudra. So it will know the 5-day mean state of ACE's 6-hour surface conditions. And then from the ocean to the atmosphere, we pass SST and the ocean grid cell fraction. And these are both important for determining where exactly on the surface of the Earth ACE will predict the temperature versus where it will just take the predicted sea surface temperature that comes from Samudra. So in terms of actually coupling these things, we have a two-stage process where we start with pre-training in uncoupled mode, and then we do some coupled fine-tuning. So uncoupled mode works very similar to the original ACE2 work and the original Samudra work, and that some boundary conditions are going to be just given as prescribed forcings, inputs to the model, and then the model will advance its own state forward in time based on those prescribed forcings. So in the case of the atmosphere is taking 6 hour steps forward in time, and all of these steps are being forced by the 5-day updates of SST and sea ice. So this is somewhat different from how ACE actually was trained originally, in which it was seeing the 6-hourly updating SST and sea ice. But here, since we won't have that when we actually couple things and Samudra is outputting 5-day time steps, we do the uncoupled pre-training with this 5-day mean. And then similarly for the uncoupled ocean, training Samudra, the difference being that now we are taking 5-day average of the surface fluxes as separate components and passing those to Samudra. And then it's also outputting the sea ice. And then to actually couple these things, I very much simplified the picture here, but we essentially just superimpose A and B so that first the atmosphere from some initial condition will step forward 6 hours at a time until it reaches 5 days. Then we'll compute a 5-day average of the variables that we need to force Samudra at the ocean surface. And at that point, we take a 5-day step forward in time and update the ocean state. And it proceeds in this way autoregressively, 5 days at a time, to output a simulation of 200 or hundreds of years. And I just want to echo what Lucas said in that a huge amount of work goes into the data preparation and training and making sure that the atmosphere and ocean training in uncoupled mode are compatible so that they can be coupled together with low biases and then fine-tuned without a huge amount of trouble. And this really is the hardest part and the part that sort of takes the most work in doing this sort of AI emulation of climate models. Jumping into the results a little bit here. So I'm happy to say that Samudra is stable and has similar timing biases to the uncoupled component emulators. So here, Samudra is shown as a red line, and then you have uncoupled ACE2 for pre-training as a green line, and uncoupled Samudra as a blue line, and then CM4, the reference simulation, is this black dash line. And you can see, like, focusing here on the sea ice fraction in the lower right, you can see that uncoupled Samudra is almost perfectly tracking the sea ice fraction global annual time mean here from the reference CM4 simulation. And this is really indicative of how that particular output, the sea ice fraction, is perfectly determined by the boundary forcing conditions that it's being given when we do uncoupled pre-training. And then we break that perfect alignment when we do the coupled stepping. And you can see no longer, like, very quickly, the atmosphere will decorrelate in time with CM4, which is what we'd expect since it's completely has its own internal variability and will lose prediction skill fairly quickly on weather timescales. And at that point, the sea ice fraction, other fields that are very determined by the state of the atmosphere in the ocean, are going to sort of drift away from CM4. But in terms of the spatial pattern, bias patterns, here I'm just showing precipitation can see the biases are fairly low, like 2 millimeters per day, and similarly for the surface temperature, which is globally predicted here. So both over land and then over ocean, the surface temperature is coming from Samudra. And yeah, so prognosis sea ice is one thing that we modified by adding to Samudra. And we're happy to see that Samudra exhibits a highly accurate seasonal climatology of the sea ice fraction, both in terms of the seasonal cycle and then also the time mean distribution. This is over a 40-year simulation, has very small biases for sea ice. And this is a very important field because this will determine exactly where ACE2 is predicting the surface temperature over sea ice, or just fully getting the surface temperature of the sea from Samudra. So that's an important field that we want to match. And we also see that in terms of the ocean vertical structure, Samudra does a very good job of emulating CM4. Has a low bias in the time mean. Here I'm showing the Atlantic meridional overturning circulation over a 200-year simulation. And so here's this time series of that showing the anomaly of the AMOC. I think this is the maximum value at maybe 30 degrees north. And luckily, Samudra has a reasonable variability that we would expect for AMOC. And in terms of the time mean over 200 years, sorry, the biases are very small compared to the mean state of the AMOC. So this is a very important measure of the ocean circulation in the Atlantic that luckily is captured well by both Samudra and Samudrace. One other important phenomenon that comes out of coupling the atmosphere and the ocean is the El Nino Southern Oscillation. And so this is something that if you were to look at this Nino 3.4 time series, so here in the black line, I'm showing what this looks like in CM4. So this is something similar to SST anomalies in the Pacific, averaged over a particular region. You can see that CM4 has a good amount of variability over time over the 200-year simulation. And Samudrace is able to realistically capture much of this variability. But we can sort of dig into this a little deeper and look at the power spectrum of these lines. And you see that in some cases, for periods longer than about 4 years, the power really drops off. So Samudrace is tending to underestimate some of this low frequency variability on timescales longer than 4 years. But in terms of the sort of spatial pattern, spatial structure, here I'm showing the precipitation regressed on this Nino 3.4 index, and more, at a broad level, Samudrace is capturing the spatial structure that we hope it would. So yeah, ENSO extremes in particular are challenging. So here I'm showing again, now zoomed into just 40 years, which is from the held out set, not trained upon at all when training Samudrace. And I'm showing an initial condition at the beginning of that 40-year period, at the very end of the 200-year simulation, what CM4 looks like for the Nino 3.4 index and the corresponding Samudrace Nino 3.4 index. And so you can see that Samudrace is sort of missing some of the extremes of the warm ENSO conditions, as well as the cold ones. But this isn't just a problem for Samudrace. It's also, I think, more broadly a problem for this type of machine learning. And our baseline here is another AI emulator called BLESIM from from Dale Duran's group. And you can see that this model is a 3D atmosphere coupled to a SST alone, so the sea surface temperature, without any 3D structure in the ocean. And it's has somewhat even less variability in terms of extremes than what we're capturing. So a lot of work to be done for sure in this respect, but some progress being made here. And then we can also look at some of like the vertical structure of the response of the potential temperature anomalies to the Nino 3.4 index, which again, the Nino 3.4 index is computed just from the very surface. And then here I'm showing the full depth up down to 300 meters. And the bias is looking pretty okay, but if you're familiar with sort of looking at this sort of a plot for ENSO, you'll probably recognize this La Nina-like pattern that Samudrace is missing. But yeah, I think some encouraging work here. This is a little bit different from what Lucas talked about in the sense that we're really comparing directly to a climate model simulation. And we obviously want to keep improving upon what we've started with here, but this is encouraging start, I think. So just to wrap up here, Samudrace is an AI emulator of coupled global climate models, which was trained on 150 years of outputs from the GFD LCM4 simulation with pre-industrial CO2 concentrations. Like traditional coupled GCMs, the components of Samudrace were developed independently by distinct teams and then coupled via fine-tuning. And yeah, we get very quick and efficient simulations on a single GPU, able to simulate 800 years per day. And all code for training and running Samudrace will be released in the coming weeks via our open source GitHub repo. We also have a preprint here, which I encourage you to take a look at for more of the details of what I went over quickly in this talk. And yeah, finally, I just want to thank all of our collaborators from GFDL and M² lines, without whom, of course, this work wouldn't be possible. So thank you so much.
Great. Thank you, James, for that great presentation. We already have some questions rolling in, but yeah, feel free to enter them in the question panel. So our first question comes from Vishnu from IITH in India. First, Vishnu says, very cool model name, by the way, Samudra. How do you ensure that the atmosphere and ocean temperature profiles are compatible after the coupling?
Yeah, thanks, Vishnu. Yeah, this Samudra was the name that Surya had come up with, and actually means ocean in Sanskrit. Well, that's a great question, and I think that is definitely something we're still sort of testing and looking into in terms of, is the ocean actually able to uptake the heat that it's seeing from the atmosphere? And so we already have so as I mentioned, this simulation is pre-industrial control CO2 conditions, but we do have another output from CM4 with a 1% increasing CO2. So you'd expect the atmosphere to be heating over that period. And then the big question is whether Samudrace will actually be able to uptake that heat in the ocean properly and distribute it down in a realistic way, which is a process that can take hundreds of years to play out, all the way to the very deep abyss of the ocean. So definitely a big question. I think that probably more work in terms of the architecture of the training will be necessary to make that work than what we've just been able to do here with pre-industrial control, equilibrium climate conditions. So yeah, excited to start moving in that direction.
Great, thank you. The next question comes from Fanny Lehman from ETH. You presented several models that are stable for long rollouts. Although ACE is stable, not all AI weather models are. Do you apply specific training procedures to ensure this stability, or do you have insights on what could make this ACE family of models so stable?
I think partially the stability comes from the architecture itself. So the SFNO architecture that we're using that was developed by NVIDIA was shown to be very, very stable for long rollouts. And partially that's because it's sort of respecting the spherical geometry of the globe. And so you don't have these like big buildups of errors at the poles or something along those lines. There definitely are cases where you can fall into a particular regime for the AI model weights where you see a big jump that's unphysical in one particular variable or maybe many variables. But in general, we don't see like huge blowups that you might have seen in weather models like the first version of ForecastNet or Pengu Weather, where eventually things just go off and become unstable completely. And yeah, so part of that is that we are working at 1 degree horizontal resolution, where a lot of the weather models, maybe they're working at 1/4 degree ERA5 or even higher resolution. And so there are more challenges when you go to higher resolution, just in terms of capturing the very large, the very finest details of the power spectrum of each of these fields. And you can have errors that build up and progressively, with the autoregressive stepping, become worse and worse over time. So we are helped out by the sort of the lower resolution that we're working with here. But yeah, I would certainly love to sort of develop this type of emulator that can work at higher resolution and be stable for many years or century rollouts, but TBD if that'll be possible.
Yeah, great, that makes sense. We have one more question from Will Yick from the University of Washington, and he says, thanks for a great talk. He's wondering why you think Samudrace and other models have trouble capturing extreme ENSO events. Curious if it has anything to do with the smoothing behavior of the MSE trained models.
Yeah, I think that's definitely a good hypothesis, that there could be some smoothing even at 1 degree that's going on here, that's sort of damping down some of the variability. The interesting thing is that if you actually look at something like the annual global mean time series, of the uncoupled versions of Samudra and ACE2, they tend to capture the variability in the data in CM4 really well. And then when you couple them, a lot of that variability just gets damped out. So it's almost like, you couple these two things and the models are like, wait, what are we doing? How do we talk to one another? Let's cool things down. So one possibility is that just a better sort of training procedure, or perhaps more training, would be required to get back to a state in the model weights where they can, again, produce the full range of variability that we want to see. But the way that these models are trained is, seamless weather to climate, in terms of they're really just trained with 1 or 2 steps, or maybe in the case of the ocean 4 or 8 steps of rollout, so only out to something like 20 days. And so they're never really seeing these longer term trends that you want to capture. So it is a bit remarkable that they capture any variability on the longer term scales, but yeah, a lot more work to be done there for sure.
Great, thank you. I think that brings us to time today. I'd like to thank both James and Lucas so much for giving this talk today, and I'd like to thank all of our audience for your great questions and for tuning in. Yeah, you can learn more. I put a link in the chat where you can find past webinars in this series and where this recording will appear in a couple of days. And you can learn more about NOAA's Climate Program Office and the NOAA Center for Artificial Intelligence in the other links I put in the chat. So thank you again so much for joining us. Thanks to our speakers, and we hope to see you at another webinar soon. Thanks, everyone.